Good afternoon. I'm Max Donath, and I welcome you to the Advanced Transportation Technology Seminar Series. And as we do each week, I'm going to introduce Hannah Grun, who's going to take care of some housekeeping issues, and then I will introduce our speaker. Hannah?
Thanks, Max. As you know, today we are joined by an audience via the web as well as a live audience. So for those of you who are watching online, please sign in the chat box at the upper right-hand corner and tell us the number of people who are watching from your location. We are required to report these numbers to the US DOT, so it would be helpful to have an accurate count. You can also use the chat box to enter any questions that you have for our presenter, which will be given to him at the end of the presentation. For the live audience, please hold all your questions until the end, and we will ask you to use a microphone so that those on the web can hear what you are asking. So thank you.
It gives me a great honor to introduce our speaker today. David Noyce is the Arthur Hahn Transportation Engineering Professor and Chair of the Department of Civil and Environmental Engineering at the University of Wisconsin at Madison. He finished his PhD in civil engineering at Texas A&M University in 1999, but he's actually a local kid who grew up in the Madison, Wisconsin area. Not very often that faculty end up serving at a university in the same area where they grew up. Dr. Noyce has held positions at the University of Massachusetts Amherst, at Texas A&M University, the Texas Transportation Institute. He's worked with the Illinois Department of Transportation. On an unusual direction, he developed a full-scale driving simulator laboratory with his colleague, Dr. John Lee at Wisconsin. He's a member of the Institute of Transportation Engineers. He served as the chair of the Pedestrian and Bicycle Council. He's been active in the National Academy of Sciences and the Transportation Research Board. He has chaired several NCHRP committees and panels. He won the Mikkel Award from TRB in 2002 and the Ragnar Onset Service Award to Society from the University of Wisconsin at Madison, and in particular the 2014 Patricia Waller Award from TRB for the Best Paper in Traffic Safety and Systems. He's involved with the Signal Technical Committee, part of the National Committee on Uniform Traffic Control Devices, which manages the manual, that's the national manual for uniform traffic control devices, which really oversees the standards for traffic signals everywhere in the country. He is the director of Safe4Sim, which is another university transportation center headquartered at the University of Wisconsin-Madison. And without further ado, Dr. Noyce.
Good afternoon, everybody. Nice to be here. Thank you very much for that kind introduction. I'm going to show you a little bit of red, probably more red than you care to see here when you walk into a room. But nevertheless, I hope I can keep you entertained here for just a couple of minutes as we go through the presentation this afternoon. What I'm going to talk to you a little bit about today is this long-winded title. And thankfully, Professor Donath gave me some ideas of some things of the research we've been involved with that he thought would be good from a topic standpoint as part of my presentation. So you can see what I'm going to talk to you about is a method we developed to automatically or automate the process of identification of horizontal curves using very fundamental GIS. But I'm going to tie that into some very practical applications of using that type of information and to show you how we can do a lot of different things with this information once we're able to get our hands on it and have it easily available for us to use. What I'm going to talk to you about here is not overly complicated. It's very much applied type research, not a lot of theory behind it, but yet we still need to think a little bit about it and to see how we can use it, and perhaps you'll have some ideas to help me better use this information after we're done with our talk here. So again, I'm David Noyce. As all of you know, so I assume some of you are graduate students, certainly the professors and others in the room and those online know that, in academics you don't do anything by yourself. You have to have a good research team to make things happen. And this is my team that has been very instrumental in really creating the brains and the details of some of the things I'm going to talk to you about. Richard Lee, who is now on the faculty at the University of Louisville, was key to this research, as well as two key members of my research team in Madison, Andrea Bill and Madhav Chaturi. What I also want to just briefly tell you a bit about is we have an organization where all of our research happens in transportation engineering, something that we call the Traffic Operations and Safety Lab. So the nice acronym, TOPS. Right? So those of us in Wisconsin and our clients and our DOTs in Wisconsin know about TOPS. And this research was done within TOPS, and obviously with this title that we're focusing on, the operational and safety elements. But what I like to do, when I think is important now in all of our different research applications, is to think about the human factors component. So one thing that I've done, and Professor Donath referred to it in the introduction, is taken a very traditional approach to operations and safety and blended the human approach, the human factors approach. And I know you have a nice driving simulator. In fact, I think you have a couple of them just down the hallway here. And we're no different at the University of Wisconsin. So what we learn as traffic engineers is we can't understand everything, so we partner with psychologists and human factors experts to help us in the transportation world. And it's proven to be a very effective component of the things that we do at the University of Wisconsin. In our research, and I think you all agree because you do very similar things here at the University of Minnesota. And the combination of those things is where we're going with this talk. And as Professor Donath mentioned, we're part of a similar university transportation center as you have here at the University of Minnesota that we call Safer Sim, and you can guess by the title, what are we focused on? Safety and simulation. In a nutshell, here's what I'm going to talk to you about, at least to get us started. It's something that we have called Curve Finder. And this goes back to the long title of automating very simple horizontal curve data in this GIS environment. So as you can imagine probably from the title, it's not overly complex. We're not trying to change the world here. But as you'll see, we really have a nice benefit that I think people who are using it are finding it extremely useful to make our life simpler, to get data more quickly, and to have the data that we need to make important safety decisions. So let's take a look at this a little bit. We all know about horizontal curvature, right? Very simple. We see it, we drive it, we look at it every single day. But we know when we think about traffic safety, everybody have a traffic safety background in here, at least thinking about it a little bit, right? So safety is important in everything we do in transportation now. And we know there's lots of issues to worry about in transportation safety, but horizontal curves is one of them. And every state has done research. We've done research nationally. We look at this issue all the time, and we know that, pick your numbers here in terms of how much inflated the crash rates are at these locations, but we know it's a problem, right? 1.5 times, maybe it's 4 times, maybe it's a bigger number, depending upon the research you've seen. But we know that horizontal curves, for obvious reasons, create a safety problem. So if we're going to help understand how to solve this safety problem, then what do we have to do? Well, we have to understand what is the curve information that we're dealing with. What is the data that we have to work with in order to better understand what we're doing. So what we've done is say, well, let's look at this important information related to curves, and perhaps we can integrate it into various types of databases, highway inventory type databases, and help us better identify safety countermeasures that go along with it. Okay, so that seems like a very relatively simple problem to get our hands around. Would you all agree? What have we done, or what has the world done in terms of trying to address a similar problem? Well, we live in a wonderful world of technology now, don't we? All different types of tools available to us to help solve these problems. So related to our topic here of horizontal curvature, there's lots of different sources of information now to get a bird's eye view, if you will, of this network of roadways that exist and all the different alignments that are out there in our transportation system. So we can look at satellite images. We see that online so nicely now, right, with all the Googles and the Bings of the world that provide that information to us free and easy. Very, very wonderful tool. We can use various other types of GPS survey. There's laser scanning methodologies. Back in my good old day, we actually surveyed it the old-fashioned way, right, to come up with that data. And of course, what do we know about all these different topics here that I just mentioned? It takes time, right? It takes money. They're not always as efficient as it possibly can be. But what we also know is that there's this big world of GIS out there, Geographical Information Systems. And GIS systems are pretty easy to use. And most states have them. Most states have them in a very usable format. Some are better than others. Some are linked better than others. Some have the data better connected than others. But nevertheless, GIS provides a very accessible way with the advantages that I've identified here that says in a very, very, very cost-effective way, we can get this information we're looking for and get the information we need to make important safety-based decisions. Do you all agree with that? So let's look at it a little bit further. So here's what we thought. So we came up with this acronym or this word curve finder just to define what it is that we were doing here. And again, this isn't, we're not going off a deep end here in terms of coming up with this novel idea. We just simply are saying this. What if we can automatically detect all these curves? Run a simple algorithm, detect the curves, get the curve data, and we're not spending hours and hours and days and tons of money going out and trying to survey in some way, shape, or form all these different types of data. And if we can do that, we can automatically classify curves and compute the curve data, right, that we all learned in our basic transportation engineering courses, right, the tangent lengths, the radius, the degree of curvature, all those very fundamental things that are part of every transportation course. If we can do all that in an automated way and then create the GIS information that we need in a layer that can overlay the various systems that exist here, wow, that's not bad. Pretty good stuff, right? So we'd have the information we need and we'd be able to use it in a good way. Now, were we the first to think about this? Gosh, no. Lots of people have been thinking about this, including the Federal Highway Administration. Some of you may be familiar with this model inventory or model inventory roadway element, so the acronym MIRE, and lots of information, so I just put a screenshot of the website up here, so if you're not familiar with it, you may want to go out and take a look when you have some time and Google that. But there's lots of information, and the whole idea of coming up with a set of important data that are necessary if we're going to make good safety-based decisions across our system. Okay? So we have all this, and the reason I'm pointing this out to you is we wanted to make sure if we're going to go down this road of developing something that we call Curve Finder, that we don't want to forget about these important other sources of information that exist. So we want to parallel it and use it and perhaps make it a little bit better if at all possible. So we said, well, let's look at some improved way to do it. So we certainly want to be compatible with the MIRE federal system, okay? And we certainly wanted to be able to do the same things that MIRE does, such as identifying different curve types, whether they're traditional circular curves or perhaps they're compound. We want to be able to look at the angle points. We want to look at the independence between the curves. We want to know if they're reversed or not, and all the different combinations of curvature we can have along any type of roadway that exists within our system. And again, at the end of the day, we want to be able to extract this information in an automated way, just like MIRE is designed to do, to help, at the end, be able to look at some sort of mapping situation and have the system tell us what kind of curve we have under the different types that might be available to us, and simply lay them out, right? So now, not only are we identifying the curves here, but we're also getting the fundamental curve data that we need from a geometric standpoint to make the decisions that we need to do from a safety standpoint. So far, so good. Right? Everybody with me? All right. So, we spent some time focusing on this federal database and the different types of characteristics that they're looking at. And it turns out there's over 200. It's a long list of items. And when you look at items 107 through 114, those are the ones that deal with horizontal curvature. Okay, and you can see them up here on the screen. So we wanted to be able to look at all of those, and that's what we're trying to find, right? Now, the one thing that we just simply can't do under this methodology is superelevation, right? Determine how much we're banked. So that's still a challenge. So that's every researcher has a future research component at the end of their work, right? So I will tell you right now that is one of them. How do we do that? That's a little bit more challenging. But with the ones that we can handle, including curve feature type and the degree and the radius and all the other fundamental parts, those are very doable. So what we're looking at is identifying the angle point, looking at the independence or what type of curves we have out here. Are they reverse or compound? But what's going to be the challenge? What's going to be the challenge? Well, we don't have the perfect world out there, right? Not every horizontal curve is nice and smooth. We have curves that snake, right, that aren't as easy to identify in an automated way. So we're going to have to find a way then, when we have these unequal or unregular, or however you want to describe it, compound type curve, how are we going to be able to identify that within the system? So we dug a little deeper into the GIS world, and I'll be the first one to tell you that's where my research team comes in. That's not as my in-depth expertise in understanding the ins and outs of the software. But like we say in research, you learn enough to be dangerous, right? So I can tell you a lot about it, but if you want to ask me about how to operate a GIS system, save that question for another day, because I'm not going to be able to answer that for you. Okay, but we will be able to talk about some of the details. So again, we're digging a little bit deeper into MIRE and the other things that we want to be concerned about, and it just gives us a whole array of things to say, well, if we can't make the system better than this, then why? Well, let's just stick with what we have here in this program and this database. But we thought we could make it a little bit better, make it a little bit easier, automate it a little bit, and then be able to develop different types of systems to get to this fundamental curve data that we're looking for. Okay? So Curve Finder. The bulk of it is super, super easy. What are we trying to do? Well, I'm going to work backwards, meaning at the end of the day, once we've identified this curve in our system, we just want to identify the PC, the PT, and then overlay the fundamental components of a horizontal curve, and then tell you what the radius is, what the length of the curve is, what the tangent lengths, where the PI is, etc. Right? So that's what we want. That's the data we're looking for. And in order for us to do that, we're going to have some sort of algorithm here. And this is an algorithm in and of itself in making this calculation, but that's an easy one. But we need to have some form of an algorithm here that's going to tell us what kind of curve it is. Simple horizontal curve, nice circular curve. Is it compound? Is it reverse? Is there some spacing between the curves like it's supposed to be, at least according to the geometric design manuals that we all know? So we have all these other things that we have to identify. So we need some sort of algorithm to do that. But here's the key one. The key one is the beginning, that somehow or other we got to know if is it a curve or is it not. Right? Is it a curve or is it not? So what we do know is that in these GIS databases, we have segments and we have vertices on each end of all these segments, and they're all linked together. So in some databases, we've got to spend some time with another layer of analysis that kind of makes sure that we're all linked together in a nice continuous way. So some databases need to be cleaned up a little bit more than others. But once we have this linked system that goes all the way through our roadway alignment, we can begin to look at how to connect the dots, so to speak, and what's happening from dot to dot to dot, or vertices of all these little segments in GIS, in order to determine what's happening from a curve standpoint. So again, nothing overly detailed. We're just simply going to say, well, what is the bearing angle, or what is the degree of curvature, or what is the change from one of these vertex points to the next? And simple logic. Well, if it's bending, it's likely a curve, right? If they're straight, and the bearing angle between the two is very, very small, then it's likely a tangent. So we can use that very simple concept to help identify Is it a curve or is it not? Now, what's the million-dollar question here? Anybody know? So what's the bearing angle we need to set as a threshold, right? So when is it enough of a detected bearing angle for us to know that, yep, that's a curve, or nope, it's not a curve, it's a tangent? And that's the question. I mean, so the only thing that we're really dealing with that has some sort of normalization, if you will, in the series of algorithms is identifying what that appropriate bearing angle is. And once we know that, we can be very accurate in our calculations. So for those of you who are familiar with GIS and ArcGIS type tools, what we're simply doing is developing an ArcMap type add-on that we call Curve Finder. We're building it in through a number of different packages here, and at the end of the day, we can look at these various maps and identify in an automated way where those curves are. Simple as that. So I've already showed you some of the MIRE components, so we're doing the same thing, so I think we can skip that. And at the end, again, we're doing the same type thing, now just in a more computerized, if you will, type frame and format, identifying through all the variables that were in the algorithms and the software, all the different types of curve length, curve direction, types, degree of curve, etc., all those things that we want to know. All right, well, we developed these algorithms. Got to try them, right? So we went to a couple counties in Wisconsin that had very nice GIS maps. And one of them being Adams and one of them being Taylor. We ran the algorithm. This is what we got. Well, it doesn't look like much of a piece of information to you, does it? Just some line maps with little colored dots all over them. But what we learned really quickly was, hey, this thing might actually work. You know, it's nice when research leads to something productive that you can use. And we saw really quickly that we can identify all different types of curves in a relatively efficient manner. So the question is, what is the accuracy of this and what else do we need to do to make sure that we are operating in a great way? So again, I told you this bearing angle is really the million-dollar question. So we had to spend some time then thinking about when we do have errors, what are the errors? And the one thing that we can calibrate in terms of the identification process is this bearing angle. So in other words, what is the optimal angle of detection to optimize or maximize, perhaps is the better word, the probability of detecting a curve when it is a curve and not detecting a curve when it's not. Okay? So we spent some time on that. And going back to our fundamental world of statistics and error development and all the other things you've experienced, we went back to the simple type 1 and type 2 errors. And said, well, what can go wrong? Well, we can have what we'll describe as a type 1 error where we failed to detect there was a curve. Okay? So we can have some part of the curve missing, we can have a lot of part of the curve missing, we can have most of it, or boy, we can just miss it all together. So we have some error along those lines. Or we can say we can have the type 2 error on the other side, and that's saying that a tangent section, or misidentifying, I should say, a tangent section is part of the curve, right? So in other words, looking up here and saying, you know, this is a curve, when in fact it's not. So like all things with type 1 and type 2 errors, what's the worst case scenario? Would you rather have a type 1 or a type 2? And the answer is pretty simple, right? So put this safety hat back on. If there's a curve there, boy, we better be able to identify it. We don't want to miss a curve, right? The tangent stuff we can deal with. But if a curve's there, we don't want to miss a curve. So we had to think about that very, very carefully. So we came up with several measures of effectiveness that I won't drill down to the details on for you, but simply say this, that we can look at different types of identification rates. And we can say that some percentage of the curve segments that are successfully identified, obviously that's a good thing. But then we'll relate those to the type 1 errors, and then we'll come up with another measure for the type 2 error rate, and we can then look at them both together and perhaps bring them together to help us find what that optimal bearing ratio or degree of curvature detection is. That make sense? So in a simple way, if we start to plot this out, we can say, well, and this is no surprise to you, I'm sure, that the lower bearing angles here has the highest probability of being detected, right? So if we have a set of very low threshold, anything bigger than that's going to be detected, and there's a curve there, so we have a very high curve detection rate. And it works on the opposite side with type 2 errors. That if we set the bearing angle threshold extremely high, well then we're going to definitely detect the curves, or we're going to definitely miss curve and tangent sections depending upon what the situation is we're experiencing out in the field, or with the mapping that we're using. Okay? So we can bring them together, and we looked at a number of different ways to try and unify this, but we said we want to put a little bit more emphasis on the type 1 errors because those are the ones that are critical. So we put type 1 and 2 together, and we came up with some sort of way of unifying these errors, and then we can plot it, right? So this unified error rate versus some form of bearing angle, and we can see where the error rate is minimal. So back to very fundamental minimization type applications. And depending upon where we're working, so this was a case where we looked at all the curves in the state of Iowa. So we ran the entire state, and we had thousands and thousands and thousands of curves. Well, we had in certain situations, depending upon the bearing angle, some number of this large number that we had the minimal number of errors, right? So the number of curves that we weren't able to effectively identify. So with this in mind, it started to become pretty clear that somewhere around 1, maybe 1.5 degrees, became a good location of a starting point of a bearing angle that we can use. And when we did that, so here's an Iowa set of data from the analysis we did there, and then we took that information and said, well, let's get a segment of roadway that we have ground truth on. We know the curve data, and we can compare a known set of information to what we developed in our algorithms. And when we did that, of some 249 curves, 118 of them, and we look at 90 to 90%, so this is how much the curve was effectively identified. We saw right away that, well, we may not be getting all of it, but we started to get the large percentage of curves were very easily identifiable with the databases that we had that weren't overly clean, but they were usable, and with this very simple algorithm that we developed. So again, kind of the light's going on, right, that this may be a useful tool that we can use. We looked at a number of other states, so I'll skip through all the details of each one of these, but we've now had an opportunity to work with a number of states around the country who saw, perhaps like Professor Donath did, this paper at TRB and said, well, this seems like a good idea. Let's apply it to the curve data and the GIS databases we have in our state, and does it work? So Wyoming was another one, and we again go through the same calibration process and identify about where the appropriate bearing angle is based on the roadway systems that exist in those communities. So again, through repetition, we start to drill in at the appropriate way to calibrate these models. And as we began to learn more about calibration, do we still have errors of identification, or at least in part? Yes, but we're starting to get very effective in identifying curves in an automated way. We did some additional, I should say, analysis in Iowa, and here's some more. But what you like when you do this type of stuff is a plot, if you will, that looks something like this, right? So we're getting a nice identification rate here, and I think those are things that we've already talked about before. Same way with Wyoming. Once we applied a number of ground truth related applications to it, we saw very good numbers here at the upper end. So the last thing we had to do to validate it is say, well, okay, so we've identified the curves. For the most part, we didn't get them all 100%, but we got the bulk of the information. But what was that last algorithm that we had? That last algorithm then took all that information and turned it into radius, degree of curvature, tangent lengths, all the very fundamental components of a horizontal curve, right? So when we looked at that and said, well, if we want to first of all talk about curve length here, as we've identified in a ground truth format, and what we then were able to calculate from the algorithm, if the algorithm was doing a good thing, then we would have a nice even line here, and we'd have a r squared value of 1, right? The data is all the same. And we were pleasantly surprised to see, well, we can be pretty close to the actual data with some of the calculations that these algorithms are doing. So when we looked at curve length, and we looked at degree of curvature, we looked at curve radius, getting very nice results in comparison to the actual data versus where we were identifying. So good news, right? Well, of course we had to run it in Minnesota, otherwise I wouldn't have been invited up here to talk, right? So I had to run Minnesota data, and we have talked to MnDOT a little bit about this, but have not gone through the full calibration process and trying to identify and seeing what percentage of all these curves we're able to get. But nevertheless, running the system, the interstate system, which I think at least in the data we looked at, about 700 and some curves were identified, and then some of the state route systems, approaching 3,000. On an initial scan, just using our trained eye, it seems to be working very effectively as well with the GIS database in Minnesota. And every state has I don't know what the right word is, like a flavor. A roadway has a flavor. Does that make any sense? Right? So different curves, the different design practices, different ways of laying out. A lot of that has to do with the topography and geography and all the things that exist wherever it is that you live. So every state's got a little bit different flavor of how the system works. And as I've shown you, we've looked at Iowa and Wyoming, and did a run in Minnesota, obviously Wisconsin, did some work in Florida. And we're getting the opportunity to see more and more states in terms of how their world looks and how this algorithm operates. So we believe that we have a pretty good system here. And in fact, the other states we've worked with and the other database owners we've worked with tend to agree. Is it perfect? No. We can't identify every curve. And as I mentioned to you at the beginning, many curves, as you might imagine, are not nice and clean, right? There's not the perfect horizontal, smooth curve on every single curve that exists in the roadway system. But for the most part, we can get close, right? So we can find useful tools and very, very easy to use. I mean, literally a click of the button within this GIS format, we can have all this information that we're looking for. So there's automated and highly beneficial ways to collect this, especially when we get to county and rural roadways where the state DOTs are not spending a lot of time and effort and dollars in logging this important information. Typically what we would do is look at the higher volume roadways. Often we have that data in a database someplace. But our local roads and our county roads and our rural roads are ones that we don't always have that information. So we need to continue to think about it, and we need further information to help us. Now, there's issues, right? This is where you all come in, all you smart people in the audience, right? We still got some bugs here. And we have to think about how do we solve the problems, right? And a lot of it has to do with the GIS database in terms of the segment lengths and the spacing between these vertex or the vertices, I should say, at the end of these line segments. And they vary depending upon the database. Some are very tight, 50 feet or less. Some are bigger, 400 feet or more. So depending upon the database we're working with, but maybe there's a way to add some artificial intelligence here to help smooth the curve, so to speak, when we have missing data points or things aren't quite as smooth as we like. And we can also look at situations where we have very large spacings between these points, and maybe there's a way, again, through some sort of artificial intelligence to fill in the dots, so to speak, to help reduce that information so it's able to be processed in a aerial map or some sort of image processing way to make it work. So those are the things that we're working on now. All right, so switching hats here a little bit. So now I've identified for you this very, very, very simple tool. So what do we do with it? Well, I just showed you we can come up with all kinds of curve information. We can make DOTs and county engineers and others pretty happy by saving them a little bit of work. But we're talking about safety here now, right? That's really the whole basis why we, with the Wisconsin Department of Transportation, dug into this problem. We need to know curve data to improve safety. And you can think about all the different safety things that a DOT is going to want to know. But there's other places where an automated process like this and using an aerial mapping process can be extremely beneficial. And one of the things that I've had the privilege to work on, and this is the copy of the end report, is in the tribal communities, right? Tribal communities that exist, many of them in Minnesota, many of them in Wisconsin, and as we move from here to the upper west and the southwest, lots of tribal communities in this country that have various levels of capabilities of developing the information they need to make important safety decisions on their tribal lands. So what I want to do in my last couple of minutes here, just give you a quick overview of some of the things that we did here, and I'm hoping you can see the correlation between getting this fundamental data, such as curve data, and then applying it and helping people apply it in ways perhaps that we may not have thought about before, right? So why did NCHRP, which is just a group of all the states, right? So all the states felt it was important, and we had the privilege of doing this work for them to develop some sort of guidebook to figure out how safety data can be communicated between tribes and state government, DOTs. And we all know the history, right? I mean, there's been friction between those two groups for a long period of time. Some tribes still very strongly opposed to sharing any information with the federal government in this country. Some tribes work wonderfully with their state DOTs. So there's this whole array of relationships that exist out there. But if we're going to be safety engineers and make good safety decisions, well, we need data, right? Us and academics live on data. We sleep on data. We live with data, right? Data's everywhere. But if we can't get it, boy, are we stuck, aren't we? And when we have these massive tribal lands like exists out in the western part of the state, and even locally around us here, if we have no data, that's a large component of safety-related information that we don't have, and we were not able to work with. So there is obviously importance and need and ways perhaps that we can better identify ways to timely and effectively communicate safety data on tribal lands. So that's what we tried to do. This isn't a lot of science. This is more social science in terms of, I guess I should say, this isn't a lot of quantifiable science, more social science in terms of how we're preparing this guidebook to give them some advice on how to better work together. And we spent a lot of time talking to tribal leaders, talking to state governments, spent a lot of time with the Minnesota folks here who are fantastic in helping us with this research in many states across the country. And at the end of the day, here's what we thought was important. If we're going to make this, and this is really a microscopic look at the safety problem that exists everywhere. So not only just in tribal lands, but you can think about it in counties and communities and local governments in all different places. That at some point here, we're going to have to develop some best practices based on lessons learned and literature and all those types of things about how to assess where we are, how to build these relationships, how to get the data, how to implement and use the data, and at the end of the day, again, the bottom line is improving safety, right? That's what our goal is. So I'll save, there's a ton of words on these next couple of slides, so we'll just skim these, and then we'll get to the end here so we can see if there's any questions or not. But we said, okay, well, we got to have a self-assessment. Now, it's not just the tribes we're worried about. It's the DOTs as well, right? Some of the DOTs have less than a friendly, and friendly is probably not the right word, but less than a regular cooperative opportunity of working with tribes in their particular states. Some just don't deal with it. Others have tribal liaisons and do an extremely effective and good job in dealing with all these different types of communities. So we wanted both groups to kind of self-assess. Where are we? Do we have a good working relationship, bad working relationship? And how can we work our way through all that? And then we got into different ways that if you have this situation, here are some ways you can get over it, all right? So again, with the audience, both tribal members and DOTs, and the use of the guide was relatively elementary. So we started by just a list of questions. So again, it's built like a guidebook. Anybody can pick it up and read it. You may want to look at it someday down the road if you're interested in this type of stuff. And just here are some fundamental questions. Does your agency have a standard method or process for interactions with tribal communities? Yes. Keep going. No. Well, then here's some ideas about how to solve that problem. And it goes up and down the line here with all different types of questions. And then we had self-assessment for just how the tribal communities collected their data. Some of them are so sophisticated that they blow any DOT out of the water, and some of them don't collect a lick of data. And by golly, don't even ask for it, because we don't want to know, you don't want to know, and what happens on tribal land is kind of the Vegas rule, right? What happens there stays there. And I respect that. I mean, so I'm not trying to make it sound like that's right or wrong. It's different cultures, different beliefs, different parts of history there that have come together in this world of safety that we're trying to deal with. So, excuse me, what I'll summarize here, and then we'll get to the end, is just there's lots of different sections here. So all the different chapters had different ways of how to work together. The states that are effective have tribal liaisons who can begin to develop these good relationships. And like many things in life, right, both personal and professional, it really comes down to relationships, right? When people were effectively communicating, then the data was there and the safety decisions could be improved. And we talk about other communicating things, etc. So we helped develop, in a different type of way, a mini algorithm, if you will, or some flow charts of how to improve the relationships between decision makers and tribal leaders, develop different methodologies for communicating based not only on previous literature, but some of the things we learned in talking to different folks. And then we helped develop methodologies for getting crash data, hence the connection to a thing like Curve Finder. Okay? We can help it. We can make it really easy. We're only talking about horizontal curvature stuff now, I get that. But it's a link to get the ball rolling, right? And help with all that information. And we can help identify the help identify the other parts of safety data that they need. Oftentimes it's simple working with them on developing the crash identification forms like police officers fill out regularly when we have crashes around here. We talked about different ways of sharing data. We developed methodologies for sharing, which seem pretty trivial, but yet are important through the process on how to move data once a crash or some safety element happens. How does it get its way to a database? Excuse me. We also talked about different ways of sharing the data, how we can improve that state-tribal communication. Again, the world of algorithms lives everywhere, so we can develop little flow charts here. And at the end of the day, we can have a methodology that ends up with safety improvement requests. You know, the other key component here is it's hard to get resources to improve safety if you don't know you have a safety problem, right? So what these communities are looking for, like all of us, is dollars to make safety improvements. So at the end of the day, if nothing else, there was a cost component and a benefit cost component here that would help tribal communities request the funds they need to improve safety. The last thing we did was try to improve the flow of communication. We created very, very simple brochures that we could get to the tribal leaders, the elders within the tribal community, and say, well, you may not have thought about this, but here's some things you can do to improve communication with your various DOTs or within your tribe. And like all types of PR information like this, you put in quotes from others who've done it and had success with it. Hopefully that'll stimulate you to move along in that way. And that turned out to be very effective. People are using this. Federal Highway Administration continues to hand these out, and it's included in the NCHRP report as well as case studies. So a lot of people responded well to say, well, here's what Tribe X did, or here's what DOT Y did. And it turned out to be very, very effective. Okay? So what I tried to do here was give you just a simple example, talking about another project granted, but going back to the Curve Finder component as well. There's all different ways to approach the safety problem. There's global ways, right? Thinking about the safety problem across a broad array of conditions or states or the county or the community or the country, wherever you want to look. And then there's the micro level, right? Simple horizontal curvature. And all of it's important if we're going to solve the safety problem that we have. And we all know we're heading in the wrong direction, at least in Wisconsin we are again this year. Fatalities are way up, right? So this regression to the mean thing perhaps is kind of bouncing its way back in the opposite direction. But nevertheless, we still, as a community, all of us need to work together to help solve the safety problem. In a very small way, that's what I tried to present to you here today as two simple things that we've done at the University of Wisconsin as part of the Traffic Operations and Safety Lab to work along those lines. Okay? So thank you for your attention. I only saw 3 of you sleeping, so that's a good sign here. So it's better than my lectures back at the university. So I'd be happy to entertain any questions that you have. Thank you.
Just to remind you, everybody has to use a microphone if they have a question. Any questions?
So I saw there, for some of the curves that you were having trouble tracking with your algorithm, so there were, a couple that you had a really low percentage. Were there any shared traits among those
Yeah.
I was curious about? And then other question I had is, if there are basic sort of recommendations about curves for the radius and speed about what the super elevation should be, can you start to make assumptions based off of recommendations?
Sure. Great question. So the ones that we saw that gave us the most trouble were, for lack of better description, compound curves, right? So they're snaky things. So the algorithm is saying, well, wait a second, is that a tangent? Okay, curve, nope, tangent, curve, and then it's going all over the place and can't make a decision, in its logic on trying to identify what it is. And you'll see that on rural, older roads that aren't, nicely repaved and defined in terms of those alignments. I'm sorry, I forgot the second part of your question.
Can you make assumptions about recommendations for super elevation?
Assumptions about recommendations for super elevation. Certainly the data will help you with that, right? So when you identify the curve, that's the one thing we're not able to do here with this algorithm is be able to capture that super elevation data. But yes, I think what communities can do with that data is help better identify that super elevation that needs to correspond with improving the safety on that. So am I getting at your question there correctly or no?
Well, I'm just wondering if there's a standard. So, like MUTCD or something, or is there a standard for given a certain speed and radius, this is the elevation that it should be, the super
Sure,
elevation
yeah,
should
okay,
be?
I'm with you now. So I saw Howard's raising his hand too, so he's ready to help me out. Yes, there definitely is, right? So all the way from the AASHTO guidelines, and then all states will have their own set of guidelines on what the super elevation should be for a given set of radiuses and speeds. So that data then can parallel back to help us make decisions. So most places up here, we maximize it at 6%, right? So we'll say 6% at a high speed, relatively, large degree of curvature type curve, and then we'll go down from there. You get in the south, we don't have snow and ice, then we can use a little bit larger super elevation. So hopefully that 3 times took me, but I got her. Yeah.
By the way, I sent notice out about your presentation to a whole variety of counties and state aid engineers across the state, so they may be watching all this. But let me ask you a question. How many county engineers use MIRE?
Great question. Yeah, so I think I know where you're leading with that question, and probably not many, right? So there's many sets of FHWA and federal programs that not a lot of people know about. And I'll be the first one to tell you, I didn't know about it until we started thinking about this problem. So that's a great point, Max, in dealing with all these different types of information. But yet, I would say that the Federal Highway Administration is at least pushing in the right direction, and that information, if you haven't looked at it before, I'd recommend you do, and it parallels very much with what we...
No, I'm quite familiar with MIRE and
Uh-huh.
I've read the manuals, but there's an awful lot of detail that doesn't tie in to the maps available from Nokia here, from
Right.
TomTom, from Bing, from Google. There are two different directions for quantifying roadways,
Yeah,
and one doesn't associate with the other. And that's a problem.
it's a problem.
Yeah.
That's right.
Any other questions here? Okay.
So for your tribal crash reports, so you were talking about creating sort of custom crash reports for tribal lands. How much of that is really geared toward catering toward MUC, the Model Minimum Uniform Crash Criterion? Or is it really just geared toward their needs and less toward that federal
Yeah,
criterion?
great question. What we dealt with and what we talked to many of the tribal leaders about is, you know, the muck, if you will, is a good starting point, right? So if they have no data being collected or minimal amounts of data, that provides a framework and a format that they can use to help in the data collection process. Most of the tribal communities, at least the ones that participated in our research, had some form that paralleled or was exactly the same as what the state DOTs use. Whatever, you know, every state has a little bit different one. In fact, some tribes had much more data that was automated in the process of collection. That would just, kind of blew us away, to be honest with you, in terms of the amount of data. And others, would redact a lot of data that would be personal related. So some of the parts of the data collection process were quite minimal. But that was one of the recommendations in here, is that if you don't know where to start, that's a great starting place for the data that you might want to collect. Yes, sir.
Okay. With autonomous vehicles and
Yep.
advanced infrastructure kind of being a big focus right now, do you think there's any way that there's an opportunity for research such as yours to be assisted by new vehicles' ability to both receive and send data? Whether, an example, I don't know, might be vehicles transmitting centerline data for those curves that you don't have good information for. Potentially, if they're already equipped with that, maybe that's a cheaper solution to
Absolutely.
paying someone to go survey a centerline?
Absolutely. Right? The world's going to change significantly when we get to that type of data availability, isn't it? So, we can make an argument about just what type of information, or we can at least think about better terminology, what kind of information we're going to need in order to operate in that autonomous world, right? But once we get to that point, the data flow and the amount of information that we can get, we can put this algorithm in the museum at that point, and remember the day we used to think that was important, because the flow of information data we'll be able to use will be so much better. So I think you're right on track with that. Good question.
Other questions? Anything off on the internet? No. Just want to say that one of our researchers, Kathy Quick from the Humphrey School, is actually out on the tribal lands today and couldn't be here, and she's working with several tribes and has agreements to look at the safety issues on these tribal lands. And so with that, let me point out that next week we will not have a seminar here today, and that's because there will be the TZD, or Towards Zero Death Conference, in St. Cloud. Hannah has a handout that she's going to distribute. It's out on the table at the far side. It's in St. Cloud. I believe students can go free. And Matt Richtel, I don't know how many of you know who Matt Richtel is. He's a New York Times writer and has written a book, A Deadly Wandering, about the first laws for against texting and driving at the same time. It's a very good book. Anyway, he's the plenary speaker at 8:30 in the morning in St. Cloud. So if you get up early enough next week on Thursday, you can be there in time to hear him talk. I should say, so there's no seminar next week. The week after, we're going to have a seminar by Professor Rajamani, who will be talking about magnetic sensor systems for collision prediction, traffic counting, and other applications. So that's 2 weeks from today. And 3 weeks from today, Kathy Quick will be talking about assessing roadway safety risks in American Indian reservations. So essentially a follow-up to some of what you've heard today. And if there's any questions, I'm more than happy to answer them. And if not, thank you so much for coming, and we look forward to seeing you in 2 weeks, same time, same place. If you, by the way, those students who are registered for credit, if you have any questions, you can come see me after this is over, or certainly see Hannah Grun afterwards. Thank you very much.
Thank you.